Hello, for today we're gonna tackle about the Brayton cycle. Brayton cycle was first uh, proposed by George Brayton for use in reciprocating oil burning engine that he developed around 1870. So the original Brayton engines used a piston compressor and piston expander, but more modern gas turbines engines and air breathing jet engines also follow the Brayton cycle, although the cycle is usually run as an open system and indeed must be run as such if internal combustion is used. It is conventionally assumed for the purposes of thermodynamic analysis that the exhaust gases are used in the intake enabling analysis uh, as a closed system. So, as you can see in an open cycle turbine engine, as you can see in figure 929, and as you can see in the figure 930, it's an example of a closed cycle gas turbine engine. There is a difference between two. As you can see, it's a simple explanation. For this one, is open cycle gas turbine. The process will not be like a chain, continue processing. Unlike this one, it is interconnected from 1 to 4. And unlike this one, it must be here in the column here is hanging and not connected. So gas turbines usually operate in open cycle as shown in figure 19.1 in the past, maybe uh, past engines, but is indeed as this in this present more modern engines using a closed cycle. Brayton cycle is also useful in a closed cycle turbine engine. So there are four uh, processes in a Brayton cycle, which the Brayton cycle represents the operation of a gas turbine engine. The cycle consists of these processes, which is very useful alongside a sketch of an engine, wherein we can easily understood the process or the ways uh, in determining uh, the problems involving Brayton cycles or the Joule cycle. So first I want to talk isentropic compression. Uh, it is the adiabatic or aqueous static or reversible compression in the inlet or an compressor. 2 to 3 constant pressure heat addition, also useful, also called constant pressure fuel combustion, idealized as constant pressure heat addition, isentropic expansion in a turbine, or adiabatic quasi-static or reversible expansion in the turbine and exhaust nozzle, with which we take some work out of the air and use it to drive the compressor, and second, take the remaining work out and use it to accelerate fluid for jet propulsion, or to turn a generator for electrical power or regeneration for these 3 and 4 passes. And the last is 4 to 1 because it is a closed system which is interconnected. It will again end from 1 and start again from 1. So for 4 to 1, it states that constant pressure heat rejection and cool the air at a constant pressure back to its initial condition because it is a closed system. So again, note the T's and PV diagrams of regular Brayton cycle are shown in figure 1921. So these T's and PV diagram are useful ways in determining or solving the problems, especially when difficult sketches or difficult height of a or sketch in every process of these four, uh, a little little challenging because some of this process may involve up to six. Although not just like this four, it may turn to four, five, or six, something like that. But we are focusing here in maybe four to five maximum processes. So this one, the East and PV diagrams of ideal Brayton cycle are shown in Figure 931. So you can see. Notice that all forces of the Brayton cycle are executed in steady flow devices. Those should be analyzed in the steady flow process. When the changes in kinetic potential are neglected, the energy bulk with the flow process can be expressed as a unit mass basis as. So this is our basis for the unit mass. So this one, the Q, which is the heat added, and therefore the heat transfer to the form from the working fluid are this one. This is the formula, and this one for the out. I will tell you later what is the function or the meaning of this variable. So then the thermal efficiency of the ideal Brayton cycle under the cold air standard assumptions becomes this 9 Brayton uh, W net or out over Qn, right, is equal to 1 minus the Q out over Qn is equal to 1 minus Cp uh, T minus T4 minus T1 over CPT3 minus T2 is equal to 1, and this T times T over T4 over T1 minus 1, T2 times T3 over T2 minus 1. So this is the thermal efficiency of the Brayton cycle under the colder standard solution becomes. Anyways, we can understand it more often or more harder when we try to solve this and use this kind of formula. Process 1, 2, and 3 and 4 are isentropic, which is P2 is equal to P3 and P4 is equal to P1. Thus T2 over T1 is equal to P2 over P1 is to K minus 1 over K, which is like this one, transposed to this one. So in Brayton is equal to this is the most or the common formula of the Brayton cycle. In Brayton is equal 1 minus 1 over the R over PR raised to K minus 1 over K. The idealized Brayton cycle where P is the pressure, so V is the volume, T is the temperature, is the entropy, and Q is the heat added or ejected by the system. So this is our ideal gas properties of air, which is useful because some Brayton, most often Brayton cycle uses air standard processes or the ideal gas properties of air. So kinda like this table because if for example there's a value of T, you can easily analyze the value of the pressure ratio and its volume ratio, and it's very constant values, and uh, you will not be lost in solving or seeking for its values because it's given table for free. So uh, kind of stretch our brains, kind of challenge problems. So first problem is a gas turbine power plant operating on a ideal Brayton cycle as a pressure ratio of 8. The gas temperature is 300 K at a compressor Kelvin at the compressor inlet and 1300 Kelvin at the turbine inlet. Utilizing the air standard assumptions, determine first the gas temperature at the exits of the compressor and the turbine, B the back work ratio, and C the thermal efficiency. So first we can solve for the gas temperature at the exits of the compressor and the turbine. Just here need to solve the temperature. So first get temperature for the given standard key, which is used, as you can see, it's a basis in the H1 under the PRL. According to this table, you can see the value of 10 is equal to 200.98. First, we have the example 300 for the temperature, and for the H is equal to 290. So just like that, you input kg over g as a side given there. Let RW is equal to ratio of work for the for letter B, just like so. We to solve for the as we also know that the PRL is 1.386 because it's also stated there 1.386. Yes, so you can input so you can solve for the value of the PR2. So PR2 is equal to P2 over P1, PRL is equal to A times 1.386 is equal to 11.9. So PR2, so you can also convert this to temperature just like the temperature converted to I I mean I mean the as equal value for or the ideal gas properties of air. So the as the pressure of 11.9 may be equivalent may equivalent to T2 is equal to 540 K according to the table in ideal gas properties of air, and also H2 is equal to 54425. As you can see this in the table here, it's only our basis in determining the temperature and its value for the pressure and the volume and ratio for pressure and volume ratio. So continue is first the process of 3 and 4. Why it's stated there why we use the process because isentropic expansion into a turbine, because the turbine or the process is expanding, and as you can see different kinds of pressure temperature is responsible and the expansions of the process, which is called isentropic. So T2 minus 1300 Kelvin uh, is about value of H3 is equal to 1395.87 kg per G. Also is equal to PR3 333.9. So first is the gas temperature of the A16 compressor and the turbine. So this one. This is our first question for the PR3. So we have to solve for the we know that the PR1, PR2, PR3, and PR4. That is the most important because the compressor it is very responsible in determining the any values in the compressor because it must have the pressures done here in the compressor, so that we have to look for the pressure ratio. So the PR4 is equal to P4 over P3. This formula, as you can see, as we introduced in the upper part of this uh, discussion, this is how you will need or any other things you want to, I mean any other formula you want to solve this kind of formula. So as you can see, we can we now have the PR4, so which is we have an equal temperature 770 Kelvin. H4 is 789.39 kg over G. As a turbine exit, this temperature is turbine exit, and while this T2 is a compressor exit. So our temperature is 770 K. So that is our answer. The T2 is the 540 K for compressor exit, and the temperature for is the 774 K is the turbine exit. So that is our answer for the letter A for the exits and the turbine. So B, uh, work in, work out. So for the formula for gain is equal to H2 minus H1, and the forward out is H3 minus H4. Then put the values of it, then you have to manipulate, then you will get the answer. So for the work ratio, is equal to work in over work out. So you can put the value of this work in, work out, manipulate, then you will get the answer of 0.403, and you will make it to the percentage number, or they turn it to, so that you can have it as useful in giving a specific number or value in a ratio. Uh, Commonly, the ratio is uses a percent value or percent variable. So you have 0.403 times 100 is equivalent to 40.3%. We just turn it because it's we we have to find its ratio, so that basically it will turn into a percentage, right? So for letter C, for the end and value, so it's equal to W unit over Qn for the heat addition, and this input and manipulate will answer like it 0.426. You turn it for the percentage, so that you will get 42.6% for the thermal efficiency. So we now finish for the our problem 1. So we have to tackle about problem number 2. Air enters temperature of an ideal air standards Brayton cycle at 100, keep a 200 Kelvin, which is this temperature with a volumetric flow rate of 5 meter cube per second. The compressor pressure ratio is 10. So this is the RPR. The turbine inlet temperature is 1400 Kelvin. Determine first the thermal efficiency of the cycle. B, the back work ratio. C, the net power developed in kW or kilo kilo kilowatts. So from table, IGP, ideal gas properties of air. So this is our given. So process 1 and 2 is STP. We use just like we used in the first problem. So B2, B1, PR2, PR1 is equal to PR2 times PR1. Manipulate to get the answer. Until you solve it, this this thing as you solve for the PR3. I mean for PR4. So until, so that you can get for this H and the T temperatures, and N is equal to W net over Q is equal to H3 minus H4 minus H2 minus H1 H3 minus H2. You will manipulate, put the values of it, H1, then you will get its thermal efficiency of the cycle, which is 45.7%. For the next is the work ratio. You have again use this formula, work in over work out, so you can get 39.6. For letter C, you will use the net power in kW unit, so you have to use this work option. First, you need to solve for its mass, so that you can we can find, or we can use it in helpful in finding the net work net, or the power of this work. So we use this formula and this AV over B1, which is we interchangeable, or we process, or this formula may be transposable, so we can use this formula as this one transpose letter M is AV1 V1 is minus AV1 P1 T1. So put the uh, values of this one and then manipulate, and you will get this answer, and then you will now have the value of M. So the work power is equal to this value for the M, because then just we have to manipulate this our formula, guys. This our formula. So M H3, this is a value, H4, H2, H1. So you will get a 2481 kilowatt. And then consider problem number 2. This is a problem 3. Consider problem number 2. Solve that using the constant specific heat with key for 1.4. This is our specific or constant specific heat and its properties state 2 and 4. Okay, so state 2 and 4, this means that for the temperature 2 and 4, we will that is the most important in getting and finding the uh, its values for temperature and its uh, H and P. So T2 is equal to T1, P2 over P1. As you can see, use it like this one, as we discussed here earlier. This is a process 1 and 2, 3 and 4 is entropic for these processes. So that this is kind of challenging for it using the constant specific heat. If the problem given here use the constant specific heat with K1.4, say, so understandable that you can use this. You will use this formula. You should use formula because, as you can see, it has a given key. So put in mind that there should be something this formula, for it has key sign here or key value here. So T2 is equal to T1. Put the values of it for the temperature 300, which is we refer this in the problem number 2, what we solved earlier. So you will manipulate and you answer. You will get 5.2. Also use the formula for the finding the T4, the temperature. So you will use now the N. You will need same as the other problems. You will manipulate and you will get the answer of 52.65% for the next. This letter B for the work ratio. You will also use this win or work in and work out, same as we try to solve the first and second problem. Manipulate and you will get this answer. This work ratio PMV exit. This is also using the jet engine, but you can use this because, as we see, we're in a Brayton cycle and is accurate to use. Manipulate, find the mass, because we know the mass already, so you will have this, put it quickly here, then manipulate, put the values of H, and then you will get the work power 2263 kilowatt. So next problem is the air is used as the working fluid in a simple ideal Brayton cycle that has a ratio of 2, a compressor inlet temperature of 300 K and a turbine inlet temperature of 1000 K. Determine the required mass flow rate of air for a net power output of 70 megawatts, assuming both the compressor and the turbine have an isentropic efficiency of first find the 1% and B 85%. Assume the constant specific heats at room temperature. So first we are going to find the process for the T2 and T4, and now it says it's stated here, assume that the constant specific heats at room, so which means like this problem, it has a given constant specific heat, which is expected that we have a value, and we should use this formula for it as a specific heat, which is the K, and the value of K is 1.4, so K minus 1 is 0.4. Then manipulate, put the value inside, you will get the 610.2 Kelvin, as well as this T4. We will use this same formula, same process. And this is our diagram. This is the T2. I mean, the T is diagram. This is our diagram here for the process from 1 to 2, 2 and 3, and 4 to 1. This is the Brayton cycle. Now this uh, the the Qn is equal to Cp is equal times T2 minus T1. So you will put the values inside, values of the Cp. Also Cp is a constant. You can see also other table, but anyways, you will I did not put here the values, but I'm sorry, I did not put, but you can try to search and you will see also the value for the Cp. Then manipulate, put the inside values, and you will get the answer of that. So next is the Q out, the EP. You will put it there, and manipulate, and you will get the answers in unit Q out. Simples principles of the work equal the total quality of the work, which means the work out minus work in is equal to 510.84. Put the values of this out in. It is also used this Q is equal to W. So this same, so 109.40 G. And for the last problem is if it's at 85%, so you will use 85% of that, so 7,000 over 67.5, and then you will get the 10,370 because it's 70,000, then 85% of that, the 85% of the unit out, so you will use as 1,037. So next is the stationary gas turbine power plant operates on a simple ideal Brayton cycle with air as the following fluid. The air enters the compressor at 95 kilopascal and 290 Kelvin, and a turbine at 760 kilopascal and 1100 Kelvin. Heat is transferred to air at a rate of 35,000 kilojoules per second. Determine the power delivered by this plant. The first question is assuming the constant specific heat at room temperature, and the second thing we need to solve is accounting for the variation of specific heat values with temperature. So first, determine the power of delivered plant, assuming the constant specific heat. So again, we'll use this formula. The T2 is equal to T1 over P over P1. I mean P2 over P1 raised to K minus 1 over K, because as you can see this there are assumptions here, the specific heat with temperature. So we shouldn't use this key. We have no choice because it is given. So first, this is our diagram to run this diagram here. So first we have to solve for that, for the temperature 2 and 4. After manipulating, you have to solve for the work net out, for the temperature PR2, and for the PT. First, for the work net out, same as a while ago. Work net out or work net, totality of work is equal simply as work out minus work in, at this one, like this one. So manipulating, you will get answer. For the T1 toilet key, is for its value of H1 on PR1 is equal to 290 or 1.2. We have to refer this in the ideal gas law or impact. Then PR2 is equal to P2 or P1 times PR. Manipulate for the values, you'll get the answers, as well as this T3, PR4, and for the N, 1 minus Q out over Q1 is equal to 1 over Cp. T4 minus T1, Cp3, 3 is equal to T2 is equal to 1 minus T4, T1, T3 is minus T2. Manipulate for its values, you will now get the final answer for this A, and then letter B. Is the working out for 1671. So this is our letter B. Letter B, right? You have to solve the variable specific heat. Yes, I mean assumptions of variable specific heat. We should refer in this ideal gas properties of air. So manipulate, put the values, check values of it. So you will get these answers. First, I mean the second, we use for the power delivered for the A and B. Same process for A and B, and how in getting the power. And next is the next problem is air enters the compressor of a gas turbine engine at 300 K and 100 kPa, where it is compressed to 700 kPa and 580 K. Heat is transferred to air in the amount of 950 kg or kg before it enters the turbine. For turbine efficiency of 86%, determine A. First, the fraction of the turbine work output used to describe the compressor, and for B, the thermal efficiency, assume variable specific heat of air. So the solution: an actual gas turbine power plant operates at specified conditions. The fraction of the turbine work output used to drive the compressor and the thermal efficiency are to be determined. Assumptions 1. Steady operating condition exists. 2. The air standard assumptions are air is applicable. 3. Kinetic and potential energy changes are negligible. And lastly, air is an ideal gas with variable specific heats. So that are 4 assumptions. Then the properties of air are given in the table we discussed already. First use the isentropic relations. Same process as we solved a while ago. After getting that, I will first introduce the diagram. This is our diagram, the isentropic relations. Then for A, we have to solve for the fraction of turbine work used to drive the compressor. So by output we have to solve for the output for N, which is work in over work out is equal to 52.7%. That is the fraction of turbine work output used to drive the compressor. Next is for the letter B, same process. For the N, W net over N, we can get 27%. So next problem. Repeat problem 978. This is our problem 978. Can the is this can this mean wait, repeat the problem for this one. Problem 1, 2, 3, 4, 5, 6. Not 7. It's problem 6 using the specific heat. This is our problem 7. So now using constant specific heat at room temperature, it's there are assumptions here. The properties of constant specific heat at room temperature. So we should now use the formula using the K minus 1 over K. So first thing, a gas turbine power plant operates at specific conditions. The fraction of the turbine work output used to drive the compressor and the thermal efficiency are to be determined. Properties of air temperature, Cp is equal to 1.005 for the kg over times K, and K is equal to 1.4. So use the constant specific heats. First you have to solve for the pressure ratio, which is 7, because 700 over 100 is 7, because P2 is 700 and P1 is 100. As you can see, manipulate it using this formula. Manipulate, you have to put the values. We know that the key is 1.4, so manipulate until you get the 874.8 key. For solving for the W and W out is a formula H2 minus H1 is equal to Cp T2 minus T1. Then manipulate, put its values as well as this work out is same formula. You will gather these answers. Then for the N, W in minus W out, manipulate, you will get this answer. And for the win out, W net out is equal to out, or the totality of the work is equal to W out minus W in is equal to 562.2 minus 281.4 is equal to 280.8 kg over kg. This is our final answer. Next question is a gas turbine power plant operates on the simple Brayton cycle with air as the working fluid and delivers 32 megawatts of power. The minimum and maximum temperature in the cycles are 310 and 900 Kelvin, and the pressure of air at the compressor exit is 8 times the value of the compressor inlet, assuming an asymptotic efficiency of 80% for the compressor and 86% for the turbine. Determine the mass flow rate of the air through the cycle. Account for the variation of the specific heats with temperature. So our solution here is a 32 megawatt gas turbine power plant operates on a simple Brayton cycle with air as the working fluid. The mass flow rate of this air through the cycle is to be determined. First assumptions is steady operating conditions exist. 2. The air standard assumptions are replicable. Kinetic and potential energy changes are negligible. Air is an ideal gas with variation specific. beam. So first, you have to solve for the T1 so that we can know the value of this H1 and the PR1, and we can use this method in finding by using the ideal gas properties of air. Next is to solve for the PR2. The same process as we will go. I think you are very master of doing this. I put the formula and you get the answer. This or diagram. This is an variable specific heats. So next, after you finding the T2 and PR4, you will solve for the totality of the work. Work net out is equal to N times H3 means H4S H2S minus H1 over N. We can use the H here because this is the true isentropic process. So we know that the maximum number is not the 3 here. The 3 here, but in the length is the 4. So it's kind of interesting of the diagram or the process of the turbine or the Brayton cycle. So we can have the value of M. By pulling it out, we know that the value of M is now is 386 kg per second. So this is our answer. Then next question is repeat. Next question is the repeat problem number 8 using a constant specific heat at the room temperature. So now as we know, if there will be a constant specific heat given as assumptions, we should consider and use this formula. Okay, it's very useful. We should know that for the temperature we have to use this same process, manipulate, put the values, and you get the for the T2 station for the temperature 4 also. That's our diagram, same diagram. The only difference is have an assumptions here that we should use the constant specific heat in a room temperature. So you have to use mass. So kind of difference of the masses here. As you it's here 796, while this one is 984.6. This mass is increasing because of the constant specific heats at room temperature. Most often it will get increases because, as we know, if there will be an specific heat or in a room temperature, there should be a more steady or increase of temperature, steady temperature to be given and be is responsible also and connected for the process or for the cycle in a turbine or in a air standard cycle or the uh, Brayton cycle. So last question is an ideal Brayton cycle with regeneration as a pressure ratio of 10 air enters the compressors of 300 key and the turbine of at 1200 key. If the effectiveness of the regenerator is 100%, determine the network output and the thermal efficiency of the cycle. Account for the variation of specific heats with temperature. The solution ideal Brayton cycle with regeneration is considered. So the effectiveness of that regenerator is 100%. So the network output and the thermal efficiency of the cycle are to be determined. Assumptions 1. The air standard assumptions are applicable. 2. Air is ideal gas with variable specific heats. Kinetic amplitude energy changes are negligible. The properties are the given for the our table there, and the analysis nothing that this is an ideal cycle, and thus that compression and expansion processes are isentropic. We have this T1 yes, so to the T1 here, so 1.36 for this 900, for this 100% remaining cycles here.